This lecture focuses on traffic characteristics. So essentially those variables that we use to measure and quantify the quality or level of service that's being provided by our road facilities, with specific emphasis on the three fundamental traffic characteristics of speed, flow, and density. After today's lecture, students should be able to describe and estimate a series of important traffic flow characteristics in addition to understanding the fundamental relationships between these three primary variables alluded to previously. And so this general field we refer to as traffic flow theory, and it can be handled in a manner that is analogous to what you may have learned in fluid mechanics. We can essentially think of traffic flowing as if it were liquid in a pipe, for example. And so there are essentially going to be two primary flow conditions that we'll deal with in transportation engineering, and those are referred to as uninterrupted and interrupted flow. And so uninterrupted flow would be focusing on road segments where traffic is continuously moving, i.e. uninterrupted. And so under these conditions, traffic would be influenced primarily by the characteristics of the roadway. So if you think about how you travel along a road, your speed would be influenced by factors such as whether there is horizontal or vertical curvature, whether there are intersections or driveways, the lengths, the widths of our travel lanes and shoulders, whether there is a median or traffic barrier present dividing the two directions of flow. And secondly, the interrupted flow case, which is where we're focusing on traffic flow when it is interrupted by traffic signals. Primarily, we're focusing on traffic signals under those circumstances. And so for the purposes of this course, we'll be focusing primarily on the uninterrupted flow condition. And so when we think about uninterrupted flow, what we are looking to do from a traffic engineering standpoint is find ways for us to measure or quantify the level of service that's being provided by a specific road facility. So for example, if we're looking at one stretch of interstate versus another, how can we say that conditions are quote unquote better on one versus the other? And so if we think about ways that we can measure or quantities that we can measure to assess how well traffic is flowing on a facility, one of the primary measures and one that we're probably most familiar with just as drivers would be traffic speed. So obviously we would quantify performance as being better if we have higher speeds. And so for our purposes, speed will be denoted as either U or S, and I will momentarily differentiate and distinguish as to when we use one symbol versus the other. So higher speeds are indicative of better quality of service. Traffic flow, so how many vehicles were actually moving along our road facility, which is going to be denoted as Q, just as we would see when we're dealing with fluid flow, as I had alluded to previously, or we can also refer to flow as volume, which will be denoted as V, and we'll see a P subscript, which we'll come back to in subsequent lectures. And so obviously the more traffic we're moving, the higher the level of flow, at least from an agency standpoint, that's providing us with a better level of service. And then lastly, density, or how concentrated traffic is. So as we get towards free-flowing conditions where there's no traffic on the roadway and service is relatively high, to very dense flow as we're approaching traffic jam conditions. And so these are our three primary service measures that we use in traffic engineering: speed, flow, and density. And density you'll see here is denoted as either K within the context of our fluid mechanics analogy, or as D in our second set of nomenclature. And so as you see here, we do have two sets of terminology. The first of those sets is what we will be dealing with in chapter 6 of the textbook. So Q, U, and K come into play here when we talk about the general underlying relationships between speed, flow, and density. And then we'll come back to these terms in chapter 9 when we return to what's referred to as the Highway Capacity Manual, and we'll deal with the second set of symbols, S, V sub P, and D at that time. And so now we will just transition through each of these three characteristics, starting with traffic speed, which you are all familiar with, hopefully. So the speed of any vehicle, I, we will just refer to as u sub I, and obviously speed is simply the distance that a vehicle is traveling during some specific time period. And so if we look at that at any instant during a vehicle's travel, we just take whatever distance a vehicle has traveled over a given time period, and that gives us an instantaneous estimate of that vehicle's speed. And so when we're trying to assess the performance of a road facility, what we like to focus on are average speeds, which give us a general assessment of how well traffic is flowing as a whole on a given facility. And so when we talk about mean speed, there are two mean speed measures that are common to traffic engineering, and those are referred to as time mean speed, which is the type of mean speed with which you will probably be most familiar, and secondly, space mean speed. And so just briefly introducing these terms, when we refer to time mean speed, this is simply the arithmetic speed of vehicles passing some given point on a road facility. So the way we calculate time mean speed is we measure the speeds of some arbitrary number n number of vehicles, and we simply add up all those speeds, divide by the number of vehicles, and so we just have a simple average then of those speeds. And so this is referred to as time mean speed, which is generally going to be expressed either in feet per second or miles per hour. And so as an example, let's say a vehicle is traveling from point A to point B. On the way from A to B, they travel this 20-mile distance at an average speed of 80 miles per hour, and then they return over that same 20-mile distance at a speed of 40 miles per hour. So the time mean speed of that round trip, obviously then, we're just observing the one vehicle. It's going 40 miles per hour in one direction, 80 miles per hour in the other. So the straight line average of that is simply 60 miles per hour. So this is the time mean speed with which you are all probably most familiar at this point. We can obviously expand this to hundreds or thousands of vehicles on the road network to take these averages over any given segment and time period. Now, one of the drawbacks to time mean speed is this is not necessarily giving us the best representation of how well traffic is actually performing on a facility, because when we measure time mean speed, we are essentially just measuring this at one spot on our road network. So one stretch, we set up a radar gun, for example, and we'll continually measure these speeds. And so one of the problems that comes into play here is that the slower moving vehicles tend to occupy those road segments for a longer period of time than the faster moving vehicles. And so as a result of this, what happens is that our time mean speed tends to introduce an upward bias, so we'll actually overestimate the overall speed of our system. And so to accommodate that, what we generally prefer as a measure in traffic engineering is what's known as space mean speed. And so space mean speed, which we're going to denote as u sub s bar, is the harmonic mean of speed of vehicles passing some point on a road segment over time. So rather than taking the speeds of individual vehicles at a given point, we're actually determining the total time period that's required for a vehicle to travel that length. So for example, we're observing some same number of n vehicles on a given length of road segment L, and we're simply adding up the time it takes vehicles to travel that segment. And so if we simply take the average of those vehicle travel times and the ratio of the total length of that segment to that average travel time, that will obviously give us a speed measure back, which will be similar but actually generally slightly lower than what we see with time mean speed. And so looking just at this general formula here, what we generally see is that these vehicles are being observed over the same length of road segment. So we can take this time, which is measured here, and that's simply a ratio of the length of that segment to the speed. So we have length in feet or miles here, we have speed in feet per second or miles per hour. And so as long as our units match between our length and speed measures here, this will give us the same quantity we see in the first formula here for space mean speed. And then lastly, you'll notice here if we have that same common roadway length in both the numerator and the denominator, those terms simply fall out. And so our space mean speed can simply be calculated by taking n, our number of vehicles, divided by the summation of 1 divided by the vehicle speed of each of those individual vehicles. So we're summing the inverse of those vehicle speeds, and that will give us that same space mean speed quantity back. And so returning to our prior example that we had looked at previously, if we're looking at this vehicle traveling this 40-mile round trip distance from A to B and then back from B to A, we know that when the vehicle is traveling 40 miles per hour, it's actually spending a larger amount of time on that road segment than when it's traveling 80. And so when calculating that space mean speed, we'll notice now that our mean speed is actually 53.33 as opposed to the 60 miles per hour we had calculated previously, due to the fact that that vehicle is on the road for a longer time period at 40 miles per hour. And so if we think about this conceptually, if you have a traffic stream and you have a large number of vehicles that are going at lower speeds, what they'll tend to do is drag down the average speed of that entire segment relative to the speeds of those faster moving vehicles. And so this is the quantity that is most widely used in traffic engineering, is space mean speed, as opposed to time mean speed, because it's giving us a better estimate of what's happening at a system level. Traffic flow, which we denote as Q, is simply measuring the rate at which vehicles are passing over any given point on a road segment during a specific time period. And so flow is simply, we take some time period T, we take the number of vehicles that pass a given point over that time period, and then that's generally going to be expressed in terms of vehicles per hour. And a related concept that we frequently utilize in transportation engineering is what's referred to as time headway, or more generally just headway. And so when we talk about headway, headway is simply the period of time it takes for one vehicle to pass a given point to when the next vehicle would pass that same point. So we generally measure this from front bumper to front bumper. And so the headway is a measure of how much time it takes between the arrival of successive vehicles. And so if we think about headway versus flow, there's going to be a natural relationship here. So if we actually take the sum of the headways for every vehicle that's passing that time point over that entire time period, that is simply going to sum up to whatever the total observation period is. So if we're out there for 10 minutes or 30 minutes or an hour, the sum of all the vehicle headways during that time period is just going to add up to whatever that total time period is. And so there's a natural relationship then between flow and headway, or average headway specifically, as we'll see here. So we know that the time period we're observing is simply equal to the sum of those headways. And so we can take our general flow relationship, which we've already illustrated as equal to the number of vehicles passing a given point over a specific time period, and we can simply sub in that summation of the headways into the denominator here. So instead of having n over t, we have n over the summation of the headways. And this obviously, in looking at this, it's the inverse of an average. And so Q is simply equal to 1 over the average headway. So sum up the headways, divide by the sample size. Our average headway is simply equal to 1 over flow. And so what that means essentially is we can go out and we can either count the number of vehicles that are passing a given point over a specific time period, or we can measure the headways of vehicles over that period, take the average, and then take the inverse of that, and those would obviously give us the same relationship. The one caveat here is we want to be careful that we're using consistent units and working in generally feet per second, which we can then convert to miles per hour, for example. So we'll just go through a quick demonstration here. So let's say, for example, if we look at the empirical data, what that suggests is that one given lane, a single lane of a freeway, is generally able to accommodate up to 2,400 vehicles per hour, roughly. And so if we look at that 2,400 vehicle per hour maximum, we want to determine, well, what's the average time headway that corresponds to that? And so 2,400 vehicles per hour, we take 1 over the average headway, and so we can directly calculate this number, which doesn't really give us a great intuitive sense. We see 0.0004167 hours per vehicle, and now we simply convert that to seconds per vehicle. And so we're just multiplying that quantity by 3,600. And so we'll see when traffic is flowing at capacity, we're basically seeing roughly 1.5 seconds between the passage of the front bumper of each successive vehicle, if we assume those vehicles are moving at constant spacing and constant speed over that time period. And we can demonstrate right here, just back calculating that if we take those 2,400 vehicles divided by the summation of their headway, so they each have that same 1.5 second headway, and that simply gives us back that 2,400 vehicles per hour for our flow rate. The third of the three fundamental characteristics, traffic density, denoted by K, is simply equal to the number of vehicles that we would observe over some segment of a given length. So if we were able to take an overhead image from satellite imagery, for example, and simply count the number of vehicles we see over a 1 mile segment, that would be our measure of traffic density. So density is simply equal to our number of vehicles divided by that length of roadway, with the common unit for density being vehicles per mile. And just as we saw with flow and time headway, traffic density has a related term called space headway, or spacing. So space headway is the actual physical distance between the front bumper of successive vehicles on the roadway. And so if we wish to measure space headway, we can simply take a given length of roadway. Generally, this is going to be in feet or miles, and simply divide by the number of vehicles that are observed over that stretch of roadway. So instead of seeing as in density, we saw vehicles per mile, spacing would be in terms of miles per vehicle. Now, given that that is generally going to be a very small unit, we typically convert that to feet per vehicle. And then we can easily transition from density to space headway by just this inverse relationship, just as we saw with flow and time headway. And so the density is simply equal to 1 over the average spacing between vehicles over a given road segment. And as a quick demonstration, we'll go through this example 500-foot segment of southbound I-35 here near Ames and calculate the density and spacing for the southbound traffic lanes. We see 2 vehicles traveling in the outermost southbound lane, 3 vehicles traveling in the inner lane. And from that diagram, we are able to calculate the density and spacing of both lanes. So starting with the southbound lane, where we saw 2 vehicles over that 500-foot distance, 2 over 500 gives us a spacing in terms of vehicles per foot. Now converting that to a per mile basis, we see we have a density of 21.1 vehicles per mile, and spacing obviously just being the inverse of that relationship, and converting it back to feet, we see that vehicles are spaced at an interval of 250 feet from one another on average. Similarly, for the inbound lane, where we had 3 vehicles over that 500-foot distance, we see a greater density of 31.7 vehicles per mile and an associated spacing of 166.7 feet per vehicle. Now, a natural question we run into is, how do we calculate some of these traffic flow characteristics? And in doing that, there are essentially 2 methods of detection which are widely utilized, presence and pulse detection. And the first of those, presence detection, we have, this is widely used, for example, at signalized intersections, where we have an inductive loop that's under the pavement, which creates an electromagnetic field. And when a vehicle approaches and passes over that point, it will basically send a message to the detector that there's a vehicle present. As soon as the vehicle clears that distance, the sensor will then deactivate. And on that basis, since we know this distance and we also know the length of the vehicle, we will be able to calculate what the speed is as a vehicle crosses over that point. So let's assume that a vehicle arrives at the front of that detector at time 0. What will happen is we see it that the sensor is activated, and then once the rear of the vehicle has cleared the detector, it is then deactivated. And since we know the length of the detector, we may know the vehicle length, and we know the period of time during which the sensor is activated, we can directly calculate the speed on that basis. And this just demonstrates how these 2 vehicles are traveling at the same speed, and if we have a 35-foot long single unit truck versus a 20-foot long automobile, we would know that at the same speed, the detector would be activated longer for the larger vehicle here, based solely on those differences in vehicle length. And in order to calculate the speeds, all we would need to do is take the vehicle length as well as the detector length, which of course is going to be fixed at 6 feet in this example, and divide that by the time during which the detector is actually activated. And so in the case of the automobile, we see a 20-foot vehicle with a 6-foot detector length. the detector is activated for 0.26 seconds, and so we have a nice clean 100 foot per second speed, which converts over to 68 miles per hour. And as I alluded to, we see the same speed for the truck, and so we'll just see a proportional difference here. We've got a 35-foot vehicle. The detector is now activated for 0.41 seconds, and we arrive at the same 68 mile per hour speed. And so this is how presence detection works. In contrast, pulse detection, you may have seen these out on some of the local roadways where we've got pneumatic tubes which function as when vehicles are passing over them, there's a pulse of air that's sent to the monitoring device that says, hey, a vehicle has passed over this detector. And so in order to obtain speed information, we need at least a series of 2 of these detectors so we could know when the front wheel hits the first detector, when the front wheel hits the second detector. And what we'll see then is a series of pulses, or what will be recorded by the monitoring device. And so let's assume the first pulse occurs at time 0. And so that's when the first detector is activated. Then the second detector is activated at some interval thereafter. So in order to calculate the speeds on this basis, we would need to know how far apart these detectors are spaced. We would also need to know the wheelbase of these vehicles, and then on that basis we can then calculate these speeds accordingly. And so we see a vehicle with a 15-foot wheelbase is going to activate the second detector sooner than a vehicle with a 30-foot wheelbase. And so this is just measuring the time from which the first axle strikes this detector to when the second axle strikes this detector. Similarly, we could just compare the times between when the first axle strikes the first detector and then the second detector and obtain similar types of information. And so speed is simply equal to the difference between the axle spacing, so the wheelbase, divided by the time between these pulses. And so consequently, in the case of a passenger car, you'll see the numbers are similar here. We have a 15-foot wheelbase and 0.15 seconds between pulses, so we get the same 68 miles per hour back. And likewise with the truck, in an assumed 30-foot wheelbase, our pulses are 0.3 seconds apart, resulting in that same 68 mile per hour difference. But we've also seen a big push towards what we refer to as intelligent transportation systems. And so when we talk about intelligent transportation systems, we have vehicles communicating with one another. We have vehicles starting to communicate with the roadside infrastructure. We are also collecting data from cell phones, where you have cell companies that are continuously monitoring vehicles through the use of cell phones. And so these different pieces of equipment are able to provide us with essentially real-time estimates of what speeds and volumes would be over our road network at any given time. And so we have some subsequent courses that you could get to in the curriculum that will delve into these in greater detail, but this is essentially where we're going with the future of transportation engineering. Is we have a very well instrumented network which is providing us with real-time feedback widely across our entire freeway system nearly at this time, and we're also seeing it more widely applied on some of the arterial and local loop road networks as well. Now, many of the quantities that we've talked about up to this point, particularly speed and flow, can be calculated directly. Density is a bit more challenging, and in order to calculate density, what we frequently work with is a quantity called occupancy. And so what occupancy is, it's a measure that tells us how long during a given time period a detector is occupied. So depending upon the size of the vehicle and its speed, we're going to see different occupancy times. And so occupancy essentially is just a measure that tells us what percentage of some entire time period t the detector is occupied by a vehicle. So in order to calculate occupancy, what we do is we take the entire observation time period and we then calculate how long that detector is occupied by a vehicle over that period. And so in order to calculate that for an individual vehicle, we simply take the length of the detector plus the vehicle length, and we see the I subscript here because each vehicle has its own unique length. And if we record the speed of that vehicle, which can be calculated using presence or pulse detection as we had seen previously, this will give us a quantity that's a fraction of a second. And so if we add up those quantities over all n vehicles and divide that by the total observation period, that will give us an occupancy, so a percentage of time during which that detector is occupied. And so if you're given the occupancy, we can actually back calculate speed, and we can use this to calculate a number of our other quantities as well, such as density. And so returning to the previous example, we had shown a demonstration with 3 vehicles traveling in the inside southbound lane of I-35. Now let's assume we observed this lane for 1 hour, so 3,600 seconds, and there were a total of 2,100 vehicles that passed through that segment, that particular lane of that segment during that 1 hour time period. If the occupancy is being reported by a 12-foot detector, and we find the reported occupancy of 0.18, which means that detector was on 18% of the time, we can then determine the average vehicle speed using the occupancy equation. So we know the occupancy is 0.18 or 18%. We know our observation time is 1 hour or 3,600 seconds. We're assuming a 20-foot vehicle length here, which is common for passenger cars, and we also know the 12-foot detector length. And so on that basis, then, we can back calculate a mean speed of those vehicles. And so this summation is done over all 2,100 vehicles. And so through this method, solving for U bar, we find an average speed of 103.7 feet per second, so 70.5 miles per hour roughly. Now, just wrapping up, we're culminating this lecture with an introduction to what we refer to as the fundamental traffic flow model, which is the basis of our traffic flow theory. And the fundamental traffic flow model relates our 3 key traffic characteristics. First of all, flow, which is denoted as Q, which is simply equal to the number of vehicles observed during a standard time period, which is typically given as 1 hour. Speed, which is just giving us details of how long it takes a vehicle to travel a specific length of road segment measured in miles per hour. And then density, which is telling us how densely vehicles are spaced, typically on a per mile basis. And so in looking at the units here, it should hopefully become clear that we can easily relate these 3 quantities to one another as taking speed times density. You'll see the miles cancel, and we're then left with flow in vehicles per hour. So we have what is referred to as our Q-UK relationship, where Q, flow, is equal to U times K, speed and density respectively. And of course, we can determine that speed is simply flow by density, and density is equal to flow divided by speed. And so this is the fundamental equation that we will build on as we move forward in this section on traffic flow theory, and it will also serve as a fundamental basis when we begin getting into capacity analysis in some of the subsequent lectures as well.